Good day, students. Welcome to mathgoodserve.com. In this clip, we're going to be going over our updated explanation on how to find finite limits algebraically. Before we get started, looking at some examples, let's go over the strategy involved in finding finite limits algebraically. Okay, step number one is identification. You have to be able to identify the type of limit you're working with in order to determine the right approach that should be implemented. Okay, we're dealing with finite limits here, so you should be able to identify a limit has been a finite limit. How do you do that? You basically look at what x is approaching. Okay, if x is approaching a constant, then it is a finite limit. If it's approaching plus or minus infinity, then it's an infinite limit. Okay. Now, after establishing the fact that the limit is finite, advance to step 2, which is substitution. In this step, you simply substitute the value that x is approaching into the function and evaluates the function using order of operations. Okay. If you end up with an indeterminate result, for example, you end up with solutions such as 0 over 0, infinity over infinity, infinity times 0, or infinity minus infinity, you go to step 3, or you apply an algorithm known as L'Hopital's rule. Okay, we'll go over this in the future when we studied derivatives. Alright, so in step 3, you basically carry out a transformation. This is basically an algebraic manipulation that enables you to eliminate or cancel out removable discontinuities. Okay, so what are the algebraic manipulations you can use to transform the problem? You can either factor and cancel out, you can rationalize the numerator denominator, or you can simplify a complex fraction by multiplying by the LCD. After carrying out that whichever algebraic approach that you carry, then you cancel out factors, and then you go back to step 2, which is substitution, and then you evaluate to see what your answer is. All right. In some cases, you might not be able to carry out any transformation. You might be able to apply a special trigonometric limit, which we will be covering in upcoming tutorials. Now, just a side note or a shortcut is that if the limit that you are dealing with is a derivative, there is no need to go through these steps. You can just simply apply the appropriate differentiation technique and evaluate the derivative at the appropriate point, okay? So we'll go over that later also, but we're just going to focus mainly on problems where we can use these strategies to evaluate the limit algebraically. Okay, so the instructions are for us to find the following limits. If they do not exist, we are to determine the one-sided limits if they exist, okay? We have our strategy guide on the side here for your reference. Problem number 1. Now, what if we were to find the limit as x approaches -2 of x to the third minus x squared plus 2x. Okay, so step 1, what kind of limit is this? We just basically focus our attention on what x is approaching, okay? Is x approaching a constant or plus or minus infinity? X is approaching a constant, so what does that make this? This is a finite limit, okay? So now that we know that we're doing a finite limit, we can go ahead and apply these rules. The steps. So step 2, we're going to just substitute the value that x is approaching into the x's, okay? So we are going to have parentheses -2 to the third power minus -2 square plus 2 times -2. All right. Now this is a simple arithmetic problem. Now that we can just evaluate using order of operations. All right, so we're going to deal with the exponents first. So -2 So the third is negative 8 minus negative 2 squared is positive 4 plus 2 times negative 2 is negative 4. And then this comes out to negative 16. Okay, so that is your limit. All right, let's take a look at problem number 2. Now, what if you were to find the limit as x approaches 2 of 5 over negative x plus 2? All right, so what kind of limit is this? If you look at what x is approaching, this is a finite limit since x is approaching a finite number. So let's advance to step 2, substitute. If we substitute, we're going to have 5 over negative 2, substitute 2 for x plus 2. Okay, so this becomes 5 over negative 2 plus 2 is 0, which is undefined. Okay, so what does this tell us? It tells us that the limit does not exist. Now, this is different from an indeterminate form. Remember, an indeterminate form involving 0 is either 0 over 0 or infinity times 0. We have a number over 0 here, so that is undefined. Okay? Now, if the limit does not exist, we are asked to find the one-sided limit to see if it exists. Now, what does that mean if a limit does not exist? If a limit does not exist in this format, that basically means that either the left and the right hand limits do not exist, only one limit exists, or both limits exist but are different. Okay, so that's the cases where the limit does not exist. All right, so let's look at the left hand limit. So the left hand limit is basically the limit as x approaches 2 from the left. Okay, all right, so we're gonna find the limit as x approaches 2 from the left of 5 over negative x plus 2. Okay, so the first thing we're going to do is clearly a finite limit. We're going to substitute. So when we substitute, we get 5 over negative, the opposite of 2 from the left, plus 2. Okay? All right, so just something to recall is that 0 from the left is basically the biggest negative number, okay? So 0 from the left is equal to negative 1 over infinity. All right, and 0 from the right, the smallest positive number is 1 over infinity. All right, so think about 0 from the left as 0.00, infinite number of zeros, 0, 1, negative from the left of 0, and then from the right you have 0.00, infinite number of zeros, 0, 0, 1 from the right. Okay, so that's what these two numbers are. Now let's go ahead and proceed with this problem. Now, in order for us to solve this, it's good to have an idea as to what 2 from the left is. So we can give ourselves a visual by drawing a number line and locate 2. This is 2. So what is 2 from the left? 2 from the left is the biggest number that's smaller than 2. You get really, really close to 2 from the left. So somewhere here, you're approaching 2, you have something like 1.99, infinite number of 9s. Okay, so that's basically what 2 from the left is. So what I'm going to do is I'm going to represent 2 from the left with this approximation right here so I can easily carry out my arithmetic. So this is going to be 5 divided by the opposite of 2 from the left, which is 1 point infinite number of 9s, just go on forever, plus 2. Okay? Now what will you get when you subtract negative 1.999999 plus 2? What do you get? You get 5 over 0.00 infinite number of zeros, 0, 1. Okay, you get a really small positive number. Alright, so how do you express a really small positive number? In fact, infinitely close to 0. 0 from the right. Okay, that's what this is. So write the denominator as 5 over 0 from the right. And then 0 from the right is the same thing as 1 over infinity. Now we can multiply the numerator by the reciprocal of the denominator. So we have 5 times infinity over 1. And your left-hand limit is infinity. Okay? Alright, let's go ahead and find our right-hand limits. The procedure is similar. So our right-hand limit is basically what the limit is as x approaches 2 from the right. Now, what does that look like? That's the smallest number that's bigger than 2, so you're getting really close to 2 from the right. It's like 2.00, infinite number of zeros, 0, 1. Infinitely close to 2 from the right, okay? So that's what we're looking for. Let's go ahead and find out what that limit is. We want to find the limit as x approaches 2 from the right of 5 over the opposite of x plus 2. This is a finite limit, so we'll just substitute. We'll get 5 over the opposite of 2 from the right plus 2. Okay? Alright, so how can we represent 2 from the right? So that we can have a visual as to how to carry out our arithmetic in the denominator. 2 from the right, we already talked about this earlier, is 2.00 infinite number of zeros, 0, 1. Really close to 2 from the right, okay? What happens when you add that to 2? The 2's, you subtract the 2's from each other and you're left with 5 over negative 0.00, an infinite number of zeros, 0, 1. Now, what kind of number is this? This is the smallest positive, the biggest negative number. You're getting infinitely close to 0 from the left. What do you get when you get, how do you express a number that's infinitely close to 0 from the left? You express that as 0 from the left. Okay? And 0 from the left is negative 1 over infinity, so we can write this as 5 over negative 1 over infinity. Then we can now multiply the numerator by the reciprocal of the denominator, and your answer is negative infinity. This is a right-hand limit. So we can clearly see why the limit does not exist, because these two limits are approaching totally different directions. The right-hand limit is going to negative infinity, and the left-hand limit is going to infinity. That is why the limit does not. Problem number 3. So for problem 3, we have to find the limit as x approaches 1 of 2x minus 2 divided by x squared minus 1. Alright, so this is a finite limit, as we can clearly see. So first step is we're going to substitute, actually the second step. So we have 2 times 1 minus 2 is equal to 1 square minus 1. Alright, if we evaluate this, we'll have 0 over 0, which is indeterminate. Okay? So what do we do when we have an indeterminate form? What we'll do is we carry out the transformation of this expression right here. I just brought back our strategy guide right here. For your reference, you see if you have a result that is 0 over 0, it's indeterminate. Okay? All right, so transformation, what kind of transformation are we going to carry out here? Well, let's see. We have the limit as x approaches 1 of 2x minus 2 over x squared minus 1. Well, we can factor here. Let's go ahead and factor and then we'll evaluate the limits. Okay, so if we factor this expression, we'll have 2 times x minus 1. And then using the difference of squares factorization, for the denominator, we have x minus 1 times x plus 1. Okay? And then what do you see happening here? X minus 1 cancels out. Now that is a removable discontinuity, so you cancel that out. Okay? All right, now we're done with our transformation. After transforming this expression right here, our new limit becomes the limit as x approaches 1 of 2 over x plus 1. Now we're going to go back to 2, step 2 in our strategy, and then substitute. Okay, so we're now going to have 2 divided by 1 plus 1, which is 2 divided by 2, and the final answer is 1. Okay, so that's what the limit is. All right, let's take a look at problem number 4. So for problem 4, we are to find the limit as x approaches 0 of the square root of 5 plus 2x minus the square root of 5 divided by x. Okay, this is clearly a finite limit. Let's go ahead and evaluate this by substitution. So we have the square root of 5 plus 2 times 0 minus the square root of 5 over 0. All right, this becomes the square root of 5 minus the square root of 5 divided by 0. And then we will end up with 0 over 0, which is an indeterminate form. Okay, this is an indeterminate form. So what do we do if we have an indeterminate result? We carry out a transformation. Okay, what kind of transformation can we carry out here? We have the radical symbol going on. Anytime you have a radical, what kind of transformation comes to mind? Rationalization, right? So we're going to rationalize the numerator. Let's go ahead and multiply by the conjugate. You get the conjugate by simply inverting the sign in the middle, so you can create a product of a difference of the factored form of a difference of squares. So this is the difference of the factored form, and we're just going to insert the sum, 5 plus 2x plus, okay, just change the sign in the middle, root 5. Whatever we multiply to the numerator, do the same to the denominator. All right, now when you simplify this, in the numerator, recall a minus b times a plus b is what? Is a squared plus, actually minus b squared. Okay, so we can apply this difference of squares expansion formula to this situation here. This is our a minus b, and this is our a plus b. So if we distribute this first outer inner last, we're going to have the square root of 5 plus 2x squared. The middle terms will cancel out, and you have minus the square root of 5 squared. All right, that divided by the denominator, which is, what is it? X times the square root of 5 plus 2x plus the square root of 5. I left out the limit. I just want to simplify this a little bit first, and then I'll put the limit back in, okay? All right, so we'll simplify that. We're going to have the limit as x approaches 0, and then this, the square and the square roots cancel each other out. We have 5 plus 2x minus 5, the same process applies here too, divided by x. Let's leave the denominator unchanged, okay? X times the square root of 5 plus 2x plus the square root of 5. Now what you notice in the numerator is the cancellation happening. These two add up to 0. And then I can carry out more cancellation, but I'll just do it step by step so you see exactly what's going on. You're left with 2x in the numerator divided by x times the square root of 5 plus 2x plus the square root of 5. We can now divide out the x's, okay? And then this becomes the limit as x approaches 0 of 2 over the square root of 5 plus 2x plus root 5. Now what did we just do? We just carried out a transformation, and it turns out that x equals 0 is a removable discontinuity. Okay, that's what was causing us to have an indeterminate result. That has been taken care of. Now we're gonna go back to step 2, substitution. All right, so substitute 0 for all the x's here. So we have 2 divided by the square root of 5 plus 2 times 0 plus the square root of 5, which equals 2 divided by the square root of 5 plus the square root of 5. That becomes 2 divided by 2 times the square root of 5. The 2's divide out. Okay, and then you have 1 over the square root of 5, which can be simplified by rationalizing the denominator, root 5, and that gives you a final result of root 5 over 5. That is your limit. All right, let's take a look at the next example. For number 5, what if we were to find the limit as x approaches 0 of 1 over 5 plus x minus 1 over 5, that entire expression divided by 5x. What if we were to find this limit? Okay, so what you notice here is this is a finite limit, okay, because there is a constant. What we're going to do is substitute. That's what you always do first, all right? So we substitute, we'll have 1 over 5 plus 0 minus 1 over 5 divided by 5 times 0. In the numerator, you have 1 over 5 minus 1 over 5 divided by 0 in the denominator, 0 over 0, which is an indeterminate form. Okay? All right. So what are we going to do here? We're going to advance to step 3. We're going to carry out a transformation. Okay? See if there are any removable discontinuities we can cancel out here so that we can have, we can determine what our limit is if it does in fact exist. Now this is a complex fraction, so the easiest way to simplify complex fractions, ensure that the numerator and the denominator are expressed as fractions. So I want to eliminate the denominators by multiplying by the LCD. Okay, so all you simply do is ask yourself, what is the LCD of the denominators in the numerator and denominator in the denominator? Okay, so in the numerator we have 5 plus x and 5, and then the denominator of the fraction in the denominator is 1. So what is the LCD of the 3 denominators? That's what we'll multiply this complex fraction by to get rid of the fractions. Okay, all right, so well, it doesn't get rid of the fractions, it just makes it less complex. All right, so the LCD here clearly is 5 times 5 plus x So what do we do with that? We multiply every single term by the LCD. Okay, so this term we multiply by 5 times 5 plus x. The denominator, the fraction in the denominator, 5 times 5 plus x. And then this term also you multiply by 5 times 5 plus x. Alright? Now look here, on this term, the 5 plus x is divide out. If with 5 over here, the 5's divide out. And then over here, you just multiply that, okay? So our limits, upon transformation, we're not done transforming it though. We have 5 minus 5. Now you have the plus times this minus here. 5 minus x. Distribute the negative. Let me put an arrow so you don't forget. This minus goes to the 5, and it also goes to the plus x. Alright? Now that divided by, in the denominator, you have, what do we have? We have 5x times 5 times 5 plus x. You don't have to factor out. You don't have to expand yet, just to see what cancels out. Okay, so I'll leave it just like this. The limit as x approaches 0. In the numerator, those 5's add up to 0. We have negative x over 25x times 5 plus x. Now what do you see happening here? You see that x equals 0 is a removable discontinuity, so we divide that out, and then we have the limit as x approaches 0 of negative 1 over 25 times 5 plus x. Now what we'll do is simply plug in 0. We're now done with our transformation, and we're now going back to our substitution, which involves plugging in the value that x is approaching into the expression. So x is approaching 0, so we have negative 1 over 25 times 5 plus 0. Alright, simplify that. You have negative 1 over 25 over 125, and that is your final answer. Thanks so much for taking the time to watch this presentation. We appreciate it. If you found this tutorial beneficial to you, please give us a thumbs up. We appreciate your positive feedback. If you have any questions about any of the examples we went through, or any problems on finite limits, just post your questions in the comment section below, and we'll be glad to help you out with that. Do not forget to subscribe to our channel for updates to other great AP Calc tutorials such as this. And also don't forget to test your skills with our interactive practice test. More clips can be found on math.serve.com. Thanks again for watching, and have a wonderful day.